Hello, it's everyone. My name is Christos Karras. Today I will present you the paper entitled An Overview of MCMC Methods from Theory to Applications. This is a joint work with my brother Aristeidis Karras and the professors Markos Avlonitis and Spyros Sioutas. Generally, sampling across distributions is a significant concept in statistics, probability, probabilistic theory, systems engineering, and any other fields that utilizes stochastic models. However, typical sampling techniques, such as the rejection sampling technique, are not capable for this task as they don't scale well with increasing dimensions. Markov Chain Monte Carlo MCMC techniques can be employed given that their advanced versions or variants are well suited for sampling from high dimensional spaces. Here we have the mathematical underpinnings for the Markov chain. So stochastic processes are a series of random variables that describe the states of potential infinitely vast state space S of a system at various points in a given time t. So only discrete time steps are considered in this case. Here we have a graphic representation of a Markov chain. So a random variable xt, it depends only on its predecessor xt minus 1 and not on any others. So with this Markov property, the structure of the dependence graph creates a chain. Hence we have the name Markov chain. So Markov chains are used to simulate stochastic processes in which the state of the next time step is determined only by a small number of prior time steps. So the manner in which the condition is attained has no bearing on the subsequent state. However, the lack of memory in stochastic system is often referred to as the Markov property shown in equation 1. So a Markov chain is composed of a collection of states S, a start distribution Qo, and the transition probabilities Pij. Here we have the Pij. Which probabilities are so basically the transition probabilities from one state to the next state at a given time step t. So take note that these transition probabilities are independent of time t in this case, implying that the temporal invariance is true. The temporal invariance is given in equation 2. So at each time step t, the stochastic process may be in just one state, which someone might not be aware of. Hence the distribution qt is introduced as a measure of probability for states where qit is the likelihood that the stochastic process in a state I belong to a state belong to the S at time step t. This is true. Equation 3 is true. So assuming that the set of elements S is finite, the transition probabilities between the states I and J can be expressed as a matrix P of this form, and the distributions can be expressed as vectors of this form. As a result, the probabilities for the next state can be determined using the current probabilities QIT and transition probabilities Pij, which are shown in equation 4. So equivalently, this can be expressed using the matrix notation qt plus 1 equals qt times p, and the distribution p don't change after each iteration, are called stationary distributions and given by that. So it's feasible to transist from any state to any other state where formally this inequality is true. The Markov chain is said to be irreducible. So this is true if the state graph of the Markov chain has high degree of connectivity. For irreducible Markov chains, a unique stationary distribution P exists. Another sufficient condition for unique P is to satisfy the detailed balance which is given by equation 5. So a state I belong to a set S is said to be aperiodic if it's feasible to return from a state I into it in any arbitrary number of steps after leaving it, as long as this number of steps is sufficiently big. Hence we have this inequality to express that. So for instance, if the state I has a loop around itself indicating that this PII is the loop and it's greater than 0, it's known as aperiodic. If this is aperiodic and irreducible, it's said to be ergodic. So regardless of the initial distribution QO, an ergodic chain always converges to P. So formally this is true. Equation 7 is true. Moving on to a graphic representation of a Markov chain with three states A, B and C highlighted with blue. So the edges are annotated with the transition probabilities Pij we introduced before. So all these probabilities of the outgoing arrows of each state sum to 1. Moving to the Monte Carlo simulations, one simulation is the approximation of the number of P, which is formally known to be close to 3.14. So Monte Carlo simulations are probabilistic processes that they use the repeated random sampling and the law of large numbers in order to approximate solutions to complex problems that there is no other approach to be utilized. So given a random variable x and then e greater than 0, which is the error probability, and delta greater than 0, the law of large number states that if this inequality is true and we have x1 sample up to xn, which are random variables and are sampled utilizing the same distribution as x, this probability inequality is true. So well-known example, as we said, is the approximation of the circular number of P by sampling n times from a square of uniform distribution with a length A. So the number of samples C are the samples that are drawn randomly and are contained within a circle with a radius of A divided by 2. So with the area of the square A square and the area of the circle named A circle, the ratio of the area equals the chance that a sample will be inside the circle. So in simple words, we have this expressed by equation 9, and we basically want to measure the samples inside the circle, and the samples outside the circle. This will give us an approximation to the number of P. So for sufficiently large n number, which is the samples that we draw for at least 1000 iterations, we have this approximation where P, the value of P, is close to 4 times the number of samples inside the circle divided by the total number of samples. This gives us the approximation of P hat, which is the value of P number. Here we have the approximation of P, which is done, as we said, by counting the samples inside the circle. So here we have the approximation of P hat, which is the value of P, by counting the samples inside the circle. So inside the circle we have 789 samples, and the total samples are 1000. For this approximation, we have the P hat value close to 3.15, which is a good approximation. Moving to the integration of Markov chain and Monte Carlo techniques, Monte Carlo techniques may be utilized with Markov chains in order to generate random samples that adhere to a specified probability distribution P. So the fundamental concept behind the famous Markov chain Monte Carlo MCMC approaches is to construct a Markov chain with a stationary distribution P that closely approximates the desired probability distribution. So after we create the Markov chain, the integration of the Markov chain with the Monte Carlo technique, the Markov chain is executed and the visited states, or a portion of them, are returned as samples. Here we have the MCMC applications, and first we have the estimation of integrals. So particularly in physics, where the Metropolis-Hastings algorithm first invented, many integrals had to be approximated, often with unknown normalization factors or distributions, in order to detect gravitational waves and other techniques that there is no prior knowledge. So multidimensional integral can be estimated using the Metropolis-Hastings algorithm. For example, when we want to estimate the value of the following integral, given by equation 11, with P being a normalized probability distribution, we utilize Metropolis-Hastings to draw samples x1 up to xn from P, which is the normalized probability distribution, and we create this estimator, the S hat. So the S hat is basically a function that utilizes Metropolis-Hastings to draw samples starting from the first up to the last one. So solving that approximation, or that estimator, as we have here, this is the estimation of S hat, which basically is the estimation of equation 12, which is basically the approximation of the integral 11. You can see that the result is the initial integral S. So a good way is to use the estimators to find a solution to a hard integral, or something that cannot be approximated in other way. So given only a function g, x, and seeking for an estimate for sg, a factorization gx, which equals fx times px, with px being a valid probability distribution, this has to be found. So alternatively, we can sample from any probability distribution hx and use the technique which is famous as importance sampling. So as gx equals hx times gx divided by hx, we have the estimator, which is s hat g, which basically is as the previous example. So again, the estimator of s hat returns us to the initial estimate for the sg. So ideally, hx is similar to gx. So this gives us a powerful method in order to approximate difficult integrals or functions that we don't have prior knowledge. So to illustrate this, an integral of two-dimensional function will be estimated, which is shown in equation 15. And we utilize the Metropolis-Hastings algorithm, which is basically the idea is to sample from a normal distribution which is centered at 0.0, and we achieve an acceptance rate of 35.1% for 200 samples and 34% for 1000 samples. So using these samples and the equation 14, which is basically the estimator, we can approximate the function. So this gives us an S hat, which is the approximation, close to 0.569, which is relatively accurate, as the exact value of S, of the initial function, is 0.5677. So as you can see, this is close to each other. Figures illustrate the Metropolis-Hastings algorithm on 200 samples, and on the right hand side we have the Metropolis-Hastings on 1000 samples. Another application of MCMC methods is the method that people interpret documents such as the jail prisoner's secret code by decrypting the code utilizing the Metropolis-Hastings algorithm. So given a text that has been encrypted by substituting other symbols Y for letters S in the underlying text, it's feasible to learn the inverse F function of the encryption function with, of course, remarkable accuracy. So by analyzing the probabilities of each character Y following another character X in English use text, someone could create a decent estimate of decode plausibility of decryption function. So as a result, a transition matrix can be learned, which is given in equation 16, and utilizing this matrix M, a measure of plausibility for a decryption function F can be defined as equation 17, where this function PL is entered into the Metropolis-Hastings algorithm as a probability function. So the proposal F prime is created from state F by randomly swapping two assignments in the initial F function. As a result, the proposal distribution is symmetrical, and the acceptance probability decreases to this, which is given by equation 18. So within 2000 steps of this run, a sufficiently good decryption function F was discovered, where the assignments are no longer changing, so the Y and X characters, indicating that the Markov chain has been converged. So this is a surprising achievement, given that there are 40 potential functions in the search space for the approximately 40 distinct characters in the typical texts, which is letters, numerals, spaces, punctuation characters, and so on. And in conclusion, Markov Chain Monte Carlo techniques seem to be quite beneficial in a wide variety of applications. Particularly, the Metropolis-Hastings algorithm is among of the top in the list of the great algorithms of the 20th century scientific computing presented in the CM News, and its versions are critical for Bayesian statistics and machine learning. However, Markov Chain Monte Carlo approaches are approximate, and as a consequence, these are not, sometimes they are not 100% accurate. So as a result, Markov Chain Monte Carlo techniques should be used sparingly and only when there are no better alternatives. Ultimately, one hot topic in 2022 is the integration of Bayesian neural networks along with Markov Chain Monte Carlo techniques, which leads to excellent results in approximation of stochastic problems. And this is something we are currently working on, the integration of Bayesian neural networks along with MCMC methods. That was pretty much it. Thank you for your attention. If you have any questions, don't hesitate to ask. Thank you.